Good evening, Vananda. Welcome to the YouTube lecture series for probability theory stochastic process. This is Dr. Ptsp, Associate Professor, Ashinga College of Engineering Technology. Today, we are going to discuss about transformation of a single random variable. Here, we see there is a x is a one random variable and y is a another random variable. Whatever the random variable x, we are going to be transformed from x to y. So that is, I am going to represent here y is equal to transformation of x. So it is represented in a block diagram format, a transformation of x, like a system, x, and its corresponding density function is fx of x, a random variable x, and corresponding density function of x of x. After transforming, we are going to get y, and corresponding density function is fy of x. It is like a Fourier transform. We are converting in the Fourier transform from time domain to frequency domain. Here also, from random variable x to, we are going to map into the random variable y. Now, mainly here, we are going to discuss about, there is this transfer function, whenever we are going to map in the random variable, the events, different events are there in the random variable. There is a one-to-one mapping. So there is a two ways we are categorizing. One is in the linear relationship between this x and y. So in this linear relationship, first case is, it is a monotonically increasing. So that means it goes on whenever x is increases and the corresponding mapping function y is also increases. The events of the x increases, the events of y is also increases. Another case is, second case is, it is a monotonically decrease. So even x is increases, that corresponding y is goes on decreases. And then we are going to see for there is a relationship between this x and y in the transformation. Now, if you see here, whenever y is equal to transformation of x, now in the random variable x, a particular event I am considering is specifically that is a x naught. So whenever we are transforming this x naught, in this we are going to get it is a y naught. So if you want to get again original variable, original event, x naught, so T inverse of y naught, you will get the original one. You see this diagram, you will get a better idea. It is a first one is a monotonically increasing function. Second one is monotonically decreasing function. If you observe here, there is a x random variable. This small x represents events in the x random variable. And we are mapping these events onto the y. So on y-axis, there is a y random variable and corresponding events are going to be represented here. Now, if you see, I want to write a probability of y less than, I am specifically selected one event on x naught that is going to be mapped onto the y naught. If you observe this one, it is a monotonically increases, x naught is increases, corresponding y naught is also increases. So in this particular event x naught, that corresponding event in another random variable y is a y naught. So because of this one-to-one mapping, the probability of y less than or equal to that particular event y naught is equal to probability of x less than or equal to that particular event x naught. So that is here we are representing like this. Probability of y means a random variable, y naught means a particular event in that random variable is equal to probability of x less than or equal to x naught. So This x naught is a event onto the x-axis. Now we know probability of x less than or equal to x or probability of y less than or equal to y is going to be right a distribution function. So the distribution function is fy of y naught, and similarly the right side fx of x naught. Now there is a relation between a distribution function and density function. So integration of density function is a distribution function. Derivative of distribution function is a density function. So the distribution function again we are rewriting like a density function. Now the limits here we are going to be considered from minus infinity to y naught, because the from that figure you see below this y naught it is going to be shaded area. So the whatever the y naught values, it is going to be mapped like this. So all from minus infinity to this particular y naught we are going to be considered. And similarly, in the x also, it is going to be right from minus infinity to x naught. So that is the formula here. Then we know what is the relation between x naught and y naught. So y naught is equal to transformation of x naught is equal to t inverse of y naught. So you substitute here wherever we have a x naught, this t inverse of y naught here, t inverse of y naught. So and then if we apply differentiation on both sides, we apply differentiation on both sides with respect to y naught, and then differentiation integration gets cancelled. Differentiation integration gets cancelled here, and wherever we have a y, we are going to be replaced with that particular event y naught. Here also, this x naught, this whatever the x naught, we have replaced with the tan inverse t inverse of y naught. So differentiation integration gets cancelled. Wherever we have a x, that x is going to be replaced with t inverse of y naught. And again, that t inverse of y naught, we are going to be, we don't know exactly this value. So that is going to be differentiated. And then this equation is a particular event. In general, we are going to be right, generalized case for any value of x or any value of y. So y naught is replaced with y. So fy of y, density function of a y random variable, transformed random variable, is equal to, you observe here, again this tan inverse of y naught I have replaced with x. We know x is equal to t inverse of y. You see here t inverse of y, and derivative of dou by dou y t inverse of y. So this is going to be right. This t inverse of y is a x. So finally, the density function of y is equal to density function of x and dx by dy. It is the relation between the density function of transformed random variable and original random variable, like input random variable fx of x. Now, if you see another case, monotonically decreases. Similar fashion, probability of y less than or equal to y naught. This probability of y less than or equal to y naught, again it is same within this duration. Within this duration, the limits are from minus infinity to y naught. But coming for this x is a x greater than x naught. Previously, x is a less than x naught. Now, please, x is greater than x. The events all are greater than x naught. So that's why whenever we are mapping probability of y less than or equal to y naught is equal to probability of x less than or equal to x naught. So this probability of x, probability of x greater than or equal to x naught. This probability of x greater than or equal to x naught, again we are writing 1 minus probability of x less than or equal to x naught. So the remaining terms all are same. Same procedure we are going to be follow, and wherever we have this probability of y by y less than or equal to y naught, or a probability of x less than or equal to x naught is nothing but distribution function of y, distribution function of x. Again, there is a relation between distribution function and density function. That is going to be right is a density function. And then we are going to be concentrated at a particular point. That point we are going to be right y naught. And if you differentiate with respect to y naught on both sides, so differentiation gets cancelled. Derivative of constant is also 0 minus. Again, there is a, whatever we have a, this x naught is going to be right t inverse of y naught. Same process. If you differentiate this one, differentiation integration gets cancelled. So whatever the x that is going to be right t inverse of y naught, and then again we are going to be differentiate with respect to y naught. Now, instead of writing a particular point, we are going to be replaced for generalized case at any point on the event. So that is going to be right. Fy of y is equal to minus fx of t inverse of y into dou by dou y of t inverse of y. So what is this t inverse of y? It is nothing but x. So Fy of y is equal to fx of x. This minus you write here minus dx by dt. So whenever it is a monotonically increases, we have a positive derivative. Whenever it is a monotonical decrease, there is a negative. So generalized case, you take a magnitude. So today, I'm going to stop this class. We will continue in the next class.